My name is Harsha, and I'm delighted to be presenting our work, IroKnight, Ownership Preserving Neural Execution for Inference Serving. LLMs have shown unprecedented capabilities. However, using LLMs today comes at the cost of relinquishing control and ownership of our data. The consequences of this loss of ownership are already substantial. Microsoft's Copilot was exploited to leak personal files, DeepSeek was caught illegally transmitting user data to third-party Chinese companies, and a bug in OpenAI's infrastructure exposed users' private chat histories to other users. Given these realities, let's look at today's landscape of confidential computing. In conventional model serving, we encrypt data at rest and in transit, but is exposed as plain text during compute. Trust execution environments have been proposed in the past, but they leak data due to fundamental design shortcomings. Fully homomorphic encryption provides some theoretical capabilities, but is not practical as it imposes unthinkable overheads. Thus, we offer a new alternative called fully state encrypted acceleration. Before walking through these existing solutions, let's formally define what it means to preserve data ownership. A system must satisfy two properties. First, each participating party must retain exclusive cryptographic control over their own data. Second, any entity observing the infrastructure state must gain absolutely no information about the underlying data. The infrastructure state encompasses all forms of storage: off-chip memory, on-chip memory, storage, and networking. Today, off-chip storage and networking are already encrypted, but on-chip storage is not. This means that pipeline registers, register files, caches, scratchpads all store plaintext data. Therefore, for a system to truly preserve data ownership, all on-chip state must also be encrypted. Trusted execution environments have been widely proposed as a solution to data privacy, but they fundamentally fail to preserve data ownership. While Ts encrypt data at the memory boundary, once data crosses onto the chip, it is decrypted and stored as plain text. Thus, by storing plain text on chip, Ts violate the necessary properties of data ownership. This storage of plain text on chip not only violates data ownership, but is also the root of vulnerabilities in TEs. In fact, since the inception of Intel's SGX in 2015, there have been thousands of papers published highlighting TE vulnerabilities. Now, NPUs further compound this problem. Unlike CPUs, NPUs have no form of trust execution environment, and they introduce a much larger attack surface. NPUs are subordinate to the system, meaning their execution is orchestrated entirely by the software stack. If that software is compromised, plaintext data on chip can be directly leaked. In fact, there are already documented software vulnerabilities across Qualcomm, Samsung, Huawei, and AMD NPUs that can be exploited to do exactly that. Let's look at the next option, which is fully homomorphic encryption. FHE does preserve data ownership. In fact, data remains encrypted even during arithmetic operations. However, to achieve this, FHE transforms conventional arithmetic into expensive polynomial operations. Each operation introduces noise into the output, and once that noise exceeds a threshold, it must be reset through an expensive process called bootstrapping. The result is orders of magnitude overhead over conventional arithmetic, making FHE theoretically sound but practically unviable. To put this into perspective, let's look at OpenAI's GPT-OSS 120B. To process a single query, a TPU takes 11.7 seconds, and an NPU is not far behind at 12 seconds. FHE, on the other hand, takes 3.2 hours for a single query, and this is an optimistic estimate. Real-world overheads are likely even larger. Similarly, a TPU consumes about 0.05 watt-hours, while FHE consumes nearly a third of a kilowatt-hour, clearly showing how far FHE is from being practical. So where does this leave us? Ts are practical but fail to preserve data ownership. FHE preserves data ownership but is completely unviable. There's a clear gap here, and that gap is exactly what we seek to fill, achieving the minimal overheads of TEs while coming as close as possible to FHE level data ownership. Fundamentally, to preserve data ownership, all stored data must be kept encrypted. FHE satisfies this, but it also performs arithmetic directly on encrypted data, which is a source of its prohibitive overheads. We take a different approach. Like FHE, we keep data encrypted across all on-chip storage, including even pipeline registers. Unlike FHE, we firmly decrypt data as it passes through the stateless combinational logic of the ALUs and immediately re-encrypt the result before it's written to any form of storage. Because these transient signals within the stateless ALUs are physically unobservable unless stored, this execution model achieves FHE level data ownership without its prohibitive overheads. We call this new paradigm for ownership preserving execution fully state encrypted acceleration. However, realizing this paradigm is not trivial. To keep all on-chip storage encrypted, we must decrypt data before every ALU operation and re-encrypt the result immediately after. Doing this naively would be prohibitive. This is because encryption and decryption are long latency operations. To encrypt or decrypt data, a cryptographic pad must first be generated, which itself takes up to 40 cycles, and then has to be XORed with the plaintext or ciphertext. This means that for every ALU operation, we must first wait 40 cycles to generate the pad and decrypt the input operands, then perform the ALU operation, then wait another 40 cycles to re-encrypt the result before writing to any form of storage. This serialization of cryptography and ALU operations severely degrades performance. To overcome this challenge, we look towards domain-specific knowledge. The acceleration paradigm itself was built by leveraging domain-specific knowledge, and we seek to do the same but for secure acceleration. To better understand this, let's look more closely at what cryptographic pad generation actually entails. Generating a cryptographic pad depends on two things: the address of the data and a write counter. This means that if we can determine these addresses and counters ahead of time, we can pre-compute the paths and completely hide the latency of encryption and decryption. This is precisely where domain-specific knowledge comes in. Addresses and fine-grained neural operators like general matrix multiplication are regular, enabling pad pre-computation. By leveraging the regularity of neural operators, we can pre-compute the cryptographic pads ahead of time, completely hiding the encryption and decryption overheads. This means that when data is read from on-chip storage, the corresponding pad is already ready, and encryption-decryption reduces to a simple bitwise XOR with the pad. This directly enables same-cycle in ALU cryptography. Data is decrypted as it enters the ALU and re-encrypted as it exits, all within a single cycle. Now let's dive into the IroKnight NPU, in which cryptography is ingrained across the entire design, supporting both GEM and non-GEM operations while also providing data integrity protection. In a conventional processing element of a systolic array, the core computation is the multiply and accumulate or MAC operation highlighted here in orange. In IroKnight, all on-chip storage is encrypted. The wait buffer and pipeline registers all hold ciphertext. To decrypt data before the MAC and re-encrypt after, we integrate a pad pre-computation unit alongside the PE. This unit runs ahead of the computation, generating pads synchronously in a looping pipeline so they're always ready when needed. As data is read from the wait buffer or pipeline registers, the pre-computed pad is XORed with the data as it flows into the MAC ALU and is similarly re-encrypted immediately after. We extend the same approach to IroKnight's vector engine, which handles all non-GEM operations. By leveraging the regularity of fine-grained neural operators, we integrate a pad generation unit in each vector lane. Thus, like the IroKnight PE, as data is read from on-chip storage, the pre-computed pad is XORed as ciphertext flows into the ALUs and is immediately re-encrypted before being written anywhere. While encryption ensures data is never exposed in plain text, it does not detect illegal modifications to the data itself. Therefore, IroKnight goes one step further by verifying the integrity of every single write to on-chip memory, providing mid-execution data authentication. To provide data integrity, we need to compute a hash for every write to on-chip memory. To calculate the hash, we walk over every 128-bit element in a block of data. Specifically, authentication Galliffield multiplies each 128-bit element by a key and accumulates the results via XORs into a hash. This process mirrors the exact multiply and accumulate flow of general matrix multiplication, except Galliffield multipliers replace conventional multipliers and XORs replace conventional accumulators. We leverage this algorithmic similarity to ingrain authentication directly into IroKnight's processing element. Galliffield multipliers and XOR accumulators are added alongside the existing MAC, and the authentication flow runs completely in parallel with the systolic flow of data. Using this parallel path, every write to the systolic engine's on-chip memory can be authenticated with minimal runtime overheads. We extend the same approach to IroKnight's vector engine. A parallel authentication path is added alongside each vector lane, where every vector write is integrity checked using the same Galliffield multiplier and XOR accumulator. With this fundamentally redesigned NPU, IroKnight adopts the strictest possible threat model. IroKnight does not place trust in anything except the ALUs and on-chip cryptographic circuits themselves. Thus, we place no trust in any other component of the infrastructure: off-chip memory, on-chip memory, storage, networking, the host CPU, etc. All of it is encrypted and integrity protected, and thus we place no trust in these components. We evaluated IroKnight across a diverse set of LLMs, including two mixture of expert models, Meta's Llama 4 Scout and OpenAI's GPT-OSS 120B. Our baseline conventional NPU follows a TPU-like configuration with the full details shown in this table. We built two configurations of IroKnight, one with encryption and one with both encryption and authentication. As expected, ingraining cryptography into the NPU increases both area and power, with IroKnight with both encryption and authentication reaching roughly 2x overhead over the conventional NPU in both area and TDP. Let's first look at IroKnight with encryption's runtime. This plot shows normalized runtime across our LLM benchmarks. The x-axis shows each benchmark LLM, with each group comparing a TPU-like NPU, an NPU-TE, FHE NPU, and the IroKnight NPU with just encryption. The y-axis shows the runtime normalized to conventional TPU-like NPU. Taking GPT OSS 120B as an example, FHE takes 3.2 hours for a single query. IroKnight, on the other hand, completes the same query in 11.8 seconds, on par with the NPU-TE and less than a 1% overhead over the conventional NPU. Now let's look at IroKnight with encryption's energy. This plot shows normalized energy across our benchmarked LLMs. The x-axis shows each benchmarked LLM, with each group comparing a TPU-like NPU, an NPU-T, an FHE NPU, and the IroKnight NPU with encryption. The y-axis here shows the normalized energy, where we normalize the conventional TPU-like NPU. IroKnight's energy overheads are limited to just 14% across all benchmark LLMs. This is because the cryptographic energy overhead is almost entirely amortized by the cost of off-chip HBM accesses. In fact, reading 128 bits of data from HBM costs 100 times more energy than just decrypting 128 bits of data. Let's look at IroKnight with authentication's runtime. As shown, even with authentication added on top of encryption, IroKnight's runtime overheads remain under 4% over the conventional NPU across all benchmarked LLMs. And finally, IroKnight with authentication's energy. Even with authentication added, IroKnight's energy overheads remain limited to just 18% over the conventional NPU, again heavily amortized by the dominant cost of reading from HBM. Thank you all for listening to my presentation. I think I have shown that there's a compelling and urgent problem in the space of privacy and ownership preserving neural execution. As LLMs gain traction in increasingly sensitive applications, it is imperative to look beyond FHE, which simply remains too impractical for real-world deployments. Toward that goal, we developed the IroKnight NPU, where plain text is exposed only ephemerally within the stateless combinational logic of its ALUs. IroKnight does not aim to replace FHE's theoretical guarantees. Rather, it innovates in architectural design to come as close as possible to FHE-level ownership without FHE's massive overheads. Thank you again for listening. You can find more information on our website here, and please feel free to email me with any questions.